All right, problem 11 from the final exam review. This one is kind of an extra challenge involving Newton's second law and circular motion and a bit of trigonometry, more than a bit of trigonometry. So see if you can follow along as we tackle this one. You have a model airplane that is flying around in a circular path. It is tied to a string that's held in place, and that string keeps it moving in a circle. But the string is at an angle from the horizontal. So there is a circular path, it's a horizontal circle. There's the radius of the circle, but we're given the length of the string and this angle between the horizontal and the angle of the string. So we're given that length of the string, we're given this tilt angle, we're told how fast that model plane is moving, we're given its mass. And we want to find how much tension there is in that string. Make sure the string is strong enough to actually hold the airplane in its circular path. So the first thing to notice is that if we want to get the radius, it is the length of the string d times cosine of this angle. That's if you view this right triangle and notice that r is the adjacent side to that angle. Okay, now here's a free body diagram for this situation. What's going on with the plane is that it's, of course, feeling gravity pulling straight down. It's feeling the tension force along the line of the string, and it's being held up in the air. It's not falling because there's a lift force between the wings and the air. That lift force is perpendicular to the wings, it's normal to the wings, so the lift force goes in this direction. You can see that that is perpendicular to the string. So if the angle of the string down here is theta, then there's also a theta between the direction of the lift force and the upward direction, which I'm calling the y direction. So those are the three forces involved. And I'm defining up as y and toward the center of the circle as r. That's my coordinate system I'm using. So we need to do Newton's second law, and there's going to be a lot of sines and cosines involved in our Newton's second law analysis. So let's try to keep them all straight. I'll start out with Newton's second law in the y direction. Let's look at the lift force in the y direction. The component of the lift is L cosine theta, because that is adjacent to the angle. So we have L cosine theta, and we have two forces in the negative y direction. We've got the y component of tension, which is T sine theta, and we've got gravity force. Because the plane is moving in a horizontal circle, it's not moving up or down, its y acceleration is zero. So the right-hand side of Newton's second law is zero. So we can write this equation, L cos theta equals W plus T sine theta. And we might want to isolate L, in which case it looks like this. I wrote it that way so I can substitute for L into my next equation, because right now we have one equation with two unknowns, both L and T are unknown. But we'll look at the other direction and we'll have another equation so we can solve our system of equations. So let's do Newton's second law in the centripetal direction. There are two forces involved in the centripetal direction. It's the centripetal component of the lift force, which gets sine and the centripetal component of the tension force that gets a cosine. And I give both of those negative signs because they're pointing toward the center of the circle. And that will equal m v squared over r. That also gets a negative sign because the centripetal acceleration is pointing toward the center of the circle. Okay. So what do we have? L sine theta plus t cos theta equals m v squared over r. Now I'm going to substitute here this thing for L. Remember, that's divided by cosine, so I just extracted that sine over cosine part out. Plus t cos theta equals m v squared over r. Now let's do some more algebra. Bear with me while we do this. I'm going to multiply everything by we'll see if you can follow what I'm doing here. I multiplied everything by cosine. And now I'll distribute this stuff. And notice that this thing sine squared plus cosine squared is equal to 1. It's a trig identity. Okay, so if we did all that algebra right, I think we're done now. All right. Looks reasonable. So I gave this problem as kind of a final challenge in Newton's second law and centripetal motion. It involves all these Newton's second law techniques we've been talking about all semester. Algebra is pretty annoying, but take some time, look at this one, make sure you understand how all the components of the forces work, how all the signs, plus and minus signs work in here. And think it's a pretty cool problem. All right.